How can a fiery universe end up at 270 degrees Celsius? If the universe began as a blazing hot Big Bang, why is almost all of it now just 3 degrees above absolute zero at about 270 degrees Celsius? There are few questions that flip our intuition about reality quite so completely. We imagine the cosmos as a place of raging stars, fiery planets, and violent explosions. But when we actually look between all of that into the vast dark in between, we find a temperature that is barely above the coldest anything can ever be. When people say space is cold, they usually picture instant freezing. Step outside a spacecraft, and you turn into an icicle in seconds, right? But while that image feels dramatic, the real story is far stranger. Space is not a giant block of ice. It's almost empty. There is hardly any matter to steal your heat. Instead, the entire universe is filled with an invisible, incredibly faint microwave glow. This glow quietly sets the background temperature of the cosmos at about 2.7 Kelvin. This means that even in the deepest voids, far from any star or planet, there is a kind of cosmic thermostat humming away at 270 degrees. So what does that actually feel like? Imagine an astronaut drifting alone in deep space, far from the warmth of any atmosphere. One side of their suit faces the sun directly. Photons slam into it, heating that surface to well above the boiling point of water. The other side faces away, staring into the black. There, with only that faint microwave background to warm it, the suit can cool toward 270 degrees. How can one person be roasted and frozen at the same time? It should be noted that this is where our everyday idea of temperature starts to break down. In a near vacuum, there is no air to conduct heat, no wind, no breeze. Only radiation in and radiation out. So it's time to find out the truth about what cold really means in a universe like this. Because that 270 degrees Celsius number is not arbitrary. It is a fossil, a clue. A leftover whisper from the birth of everything, stretched and cooled for nearly 14 billion years. By the end of this video, we will trace that whisper back to the Big Bang itself. We will see how the same physics that chills empty space also shapes black holes, limits our future technology, and points toward the ultimate fate of all stars and all life. And, optimistically speaking, 270 dig is not even the final word. There are a few rare regions out there that are even colder than the cosmic background, and here on Earth, in carefully controlled labs, we have built tiny pockets that beat the universe at its own game, reaching temperatures a fraction of a degree above absolute zero. So, let's begin with the simplest question of all. What does it really mean to say that space is cold? Why the cold of space decides the fate of everything. When we say space is cold, we are not just describing the scenery, we are describing the stage on which every star, every planet, and every form of life is forced to perform. Temperature is the backdrop of the entire universe. It decides how fast stars burn through their fuel, how quickly planets cool and solidify, and how long energy differences can exist to power complex structures, from weather systems to living cells. If the cosmic background sits at about minus 270 degrees Celsius, that is not a piece of trivia. This means it is the baseline against which everything else must struggle to stay warm. In physics, heat always flows from hot to cold, never the other way around. So the colder the surrounding universe is, the faster any object can radiate its energy away. A young, blazing star is constantly dumping light into that almost perfect dark. A rocky planet with a molten interior bleeds infrared radiation into the same cold bath. Even a black hole, through extremely slow Hawking radiation, ultimately leaks energy into this background. All of them are cooling, all of the time, into space. We actually live with this rule every day. Your refrigerator only works because it can throw heat into the kitchen air. A car engine or a power plant must dump waste heat into the environment. Our own bodies stay at roughly 37 degrees Celsius by constantly radiating and convecting heat into cooler surroundings. In the hunt for alien life, we look for planets that can do the same trick. Use a hot star, a cooler sky, and an atmosphere to move energy around. Space, at minus 270, is the ultimate heat sink. There is nothing beyond it to absorb the waste. It should be noted that this has a profound consequence. As the universe expands, that background cools and becomes more uniform. Stars will exhaust their fuel, planets will freeze, black holes will evaporate. Eventually, the temperature difference between hot and cold shrinks, until almost no useful work can be extracted. This is the so-called heat death of the universe, a state where everything is close to the same, very low temperature, and complexity has nothing left to feed on. Optimistically speaking, that future is unimaginably far away, but the current minus 270 degrees is already a clue to where we are on that long road. So it's time to find out the truth. What actually sets that eerie 3 degrees above absolute zero baseline? Why is the cosmic background not far colder after billions of years of cooling, or far warmer if stars and galaxies are constantly pouring energy into it? To answer that, we have to look for a glow that fills all of space, left over from the very beginning of time. What does temperature even mean in a near-perfect vacuum? To understand that glow, we have to ask a deceptively simple question. What does temperature even mean when there is almost nothing there? We usually treat temperature as a feeling, warm sunlight on our skin, icy air on our face, but while that works for everyday life, it hides what is really going on. At a microscopic level, temperature is a measure of the average kinetic energy of particles. The faster atoms and molecules jiggle and collide, the hotter that gas or solid is. Slow the jiggling down, and you slide toward the deep stillness of absolute zero. This means that when we talk about the temperature of air or water, we are really averaging the frantic motions of unimaginably many particles. There are trillions upon trillions of them in every breath. They bump into us, into each other, and they carry heat away efficiently. That is why a winter wind feels so brutally cold. The particles are a conveyor belt for energy. But space is different. In the hunt for alien life, we often picture starships drifting through an icy black ocean. However, in the near vacuum between planets, there are only a few atoms per cubic centimeter, sometimes far fewer. It should be noted that with so few particles, that familiar conveyor belt of collisions almost vanishes. You cannot talk about temperature there in the same way you do in a room on Earth. So how does anything cool down or heat up in such an empty environment? The answer is radiation. Every object with a temperature above absolute zero emits light, mostly in the infrared. An astronaut, a spacecraft, an airless planet's surface, all are constantly glowing in wavelengths our eyes cannot see, leaking energy into the universe. Here is the pattern interrupt. If you were suddenly exposed to space, you would not instantly freeze solid. There is no dense, frigid atmosphere to rip heat from your body. Your skin would lose energy slowly by radiating infrared light, while your blood and tissues tried to redistribute heat. You would have other, more urgent problems than temperature long before you became an icicle. Spacecraft live by this rule. In sunlight near Earth, their sunlit side can soar above 100 degrees Celsius, while the shaded side radiates toward about minus 270 degrees. Engineers design reflective blankets and radiators so that, on average, the craft settles at a stable operating temperature. So it's time to find out the truth. When we say space is at 2.7 Kelvin, we are really describing the temperature of a bath of photons, the cosmic microwave background that fills the Goldilocks zone of the entire observable universe. Optimistically speaking, that gentle glow is only the baseline. What happens when stars, planets, and blazing sunlight start to compete with it? The universe's afterglow. Why space glows at 2.7 K? So where does that bath of photons actually come from? And why is it so eerily uniform, as if the whole universe is soaked in the same invisible glow? To answer that, we have to listen to the universe's oldest light. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were using a giant horn-shaped antenna trying to clean up some mysterious noise in their data. They blamed pigeons, the hardware, even the electronics. But the hiss never went away. It should be noted that what they had really found was a faint, uniform glow of microwave radiation, arriving from every direction in the sky. This glow is what we now call the cosmic microwave background, or CMB. Think of it as a kind of fossil light, a picture of the universe when it was only about 380,000 years old. Before that time, the entire cosmos was a blinding, white-hot plasma, electrons and nuclei smashed together so often that light could not travel freely. The universe was technically full of radiation, but it was opaque, like the inside of a star. Then, expansion cooled that plasma just enough for electrons to bind to nuclei and form neutral atoms. Suddenly, space became transparent. The trapped light was released all at once, flooding the young cosmos with a brilliant afterglow. So, let's begin to see why that matters for temperature. That light started out at visible and infrared wavelengths, corresponding to thousands of degrees, far beyond anything habitable or Earth-like. But while that early flash was scorching, the universe did not stay that way. As space expanded, the wavelengths of those photons were stretched, a process we call redshifting. This means each photon lost energy, cooling from white-hot visible light down into the microwave part of the spectrum. Today, that same ancient glow corresponds to a temperature of about 2.725 Kelvin, or roughly minus 270.425 degrees Celsius. In the hunt for alien life, we often talk about a Goldilocks zone around a star. The CMB is like a Goldilocks zone for empty space itself, a kind of cosmic thermostat. Any lonely object drifting far from stars, galaxies, or warm gas will radiate its own heat away into the dark. Left alone long enough, it cools until it nearly matches this background temperature, just a few degrees above absolute zero. Optimistically speaking, you might think nothing could be colder than the universe's own afterglow. So, it's time to find out the truth. There are rare places, both in deep space and in our laboratories, that manage to slip beneath this cosmic baseline. How can anything be colder than the background of the universe itself? We will explore that mystery next. Is space really one temperature everywhere? So, if the whole universe is wrapped in this faint 2.7 Kelvin afterglow, does that mean space is basically the same temperature everywhere? Or is that just a smooth average hiding wild hot and cold pockets scattered across the cosmos? It should be noted that the cosmic microwave background is astonishingly uniform. If you fly a thermometer through the largest voids between galaxy clusters, the radiation you soak up is almost exactly the same in every direction, differing by only a few parts in 100,000. This means that, on the grandest scales, the universe really does look like a calm, cold sea at about 270 degrees Celsius. But while the background is smooth, real space is anything but calm. The moment you add a star, a planet, or a cloud of gas, you create a local environment with its own temperature rules. Near a hot star, radiation can blast matter to extreme energies. Inside a dense nebula, dust grains can shield pockets of gas. Around compact objects like neutron stars and black holes, gravity itself pumps energy into the surrounding material. Let's bring this closer to home. In the hunt for alien life, we often talk about the Goldilocks zone around a star, where a planet might be habitable. Earth lives there. Yet even in Earth's orbit, the temperature of space is not one simple number. An object in direct sunlight, with no atmosphere to spread the heat, can climb above 120 degrees Celsius. Just a few centimeters away, on the shaded side of a spacecraft, surfaces can plunge below 150 degrees. Same orbit, same vacuum, completely different thermal realities. So, let's begin to separate the background from the foreground. In deep intergalactic voids, where there may be only a few atoms in an entire cubic meter, matter has almost nothing to collide with. Left alone for billions of years, those lonely particles radiate away excess energy and drift toward the CMB temperature. Space there really does relax toward 2.7 Kelvin. Inside galaxy clusters, however, the picture flips. Gas falling into the cluster's deep gravitational well is squeezed and shocked to tens of millions of degrees. It glows in X-rays, far hotter than the surfaces of most stars, existing in the very same universe that averages just above absolute zero. Optimistically speaking, you could say temperature in space is defined less by distance and more by drama, so it's time to find out the truth. If the cosmos has this smooth, frigid background, and on top of it, such violent local extremes, which one really tells us how cold space is? And more unsettling, what happens to everything we know if that quiet 2.7 Kelvin background itself keeps changing as the universe ages? Your guide through the cosmic freezer. So if the universe is wrapped in this fading 2.7 Kelvin afterglow, who is actually guiding us through this cosmic freezer? I'm Your Name, and this is Channel Name, where we take simple questions about the universe and follow them all the way down to the deep physics underneath. Today, that question is, why is almost everything in space hovering so close to 270 degrees Celsius? And what really decides when a place in space feels scorching instead? To keep us from getting lost out there, let's lay out our path. First, we're going to slow down and ask what temperature even means when there is almost no matter. In a near-perfect vacuum, there is no air, almost no particles to bump into. So how do we define hot or cold at all? It should be noted that this is not just philosophy, it tells us why astronauts do not instantly freeze solid in the shadow of a planet. From there, we will come back home and look at how heating and cooling actually work near Earth. We will see how sunlight, infrared radiation, and that omnipresent 270-degree background tug on every satellite, every space station module, every piece of metal in orbit. This means we can use very concrete examples, like the International Space Station's radiators and insulation, to watch the battle between our warm technology and the cold universe play out in real time. Then, we will push outward. We will track how temperatures shift as we leave the protective bubble of Earth's atmosphere, cross the orbits of the outer planets, and drift into the thin gas of interstellar space. Optimistically speaking, if we understand that journey, we can start to read the temperature of almost any environment, from calm star-forming clouds to the bizarrely cold Boomerang Nebula, which actually beats the cosmic background itself. Along the way, we will keep connecting the abstract physics to real machines and real places. Deep space probes trying to stay warm at the edge of the solar system, dusty nebulae where new stars and maybe new planets are assembling, even the extreme zones near neutron stars and black holes, where radiation can push matter to temperatures that seem to contradict the quiet 270-degree backdrop. By the end, the goal is simple and powerful. When you picture any spot in space, near a blazing star, inside a glowing nebula, or drifting between galaxies, you should be able to predict whether that region is tending toward furnace-like heat or toward the cosmic background's relentless cold. So, let's begin by mentally packing a thermal suit together. As we step from one environment to the next, your intuition about what cold means in space will be challenged, broken, and then rebuilt. And in the next section, we will start with the most basic piece: how temperature works when there is almost nothing there at all, how things actually heat and cool in space. So, how does anything actually get hot or cold in a place that is almost completely empty? In a vacuum, there is no air to carry heat away, no wind, no breeze, no comforting atmosphere to share energy with. Temperature changes in space are ruled by one main process: radiation. Instead of warm air molecules bumping into you, you are dealing with photons. Objects absorb photons arriving from their surroundings, mostly from a nearby star, and they emit their own photons back out, mainly in infrared. This means every spacecraft, every planet, every grain of dust is constantly engaged in a quiet exchange of light, taking in energy and sending it away again. There is a simple rule that decides where this process stops. When the power an object absorbs from its environment exactly equals the power it radiates away, it reaches what we call radiative equilibrium. It should be noted that hotter objects radiate far more intensely than colder ones, so as something warms up, it sheds energy faster. Eventually, it settles into a stable temperature where the incoming and outgoing energy flows match. Let's make this concrete. Imagine a perfectly black spacecraft, far from any star, drifting in deep intergalactic space. There, the only meaningful radiation around it is the faint glow of the cosmic microwave background. At just 2.7 Kelvin, our craft will steadily radiate its internal heat into the darkness as infrared light. With nothing bright to warm it, its temperature will slide down until its own glow is as feeble as the background, hovering just a few degrees above absolute zero. Now move the same craft into Earth's orbit around the Sun. Instantly, the balance changes. Sunlight is now pouring in, delivering over a kilowatt of power per square meter. In the hunt for alien life, we often think about the Goldilocks zone around a star, but that same idea of balance applies here. The spacecraft will heat up until its infrared emission grows strong enough to equal the solar energy it absorbs. The result is a much higher equilibrium temperature than the lonely 2.7 Kelvin of the cosmic background. So it's time to find out the truth about surfaces. Color, reflectivity, and orientation matter enormously. A shiny, reflective panel absorbs less sunlight and stays cooler. A dark, matte radiator absorbs more, but also radiates heat away more efficiently. This means real spacecraft are wrapped in carefully engineered thermal coatings, blankets, and radiators to control exactly how they trade photons with the universe. Here is the pattern interrupt. An astronaut in space is not simply in the cold. One side of their suit might face the sun, flooded with energy from a star. The other side stares into the cosmic background's almost perfect darkness. Each side is in a different radiative environment, with its own equilibrium temperature. Optimistically speaking, the only reason the astronaut is comfortable at all is that the suit's life support system constantly shuffles heat around, fighting this split personality of roasting and freezing. In the next section, we will take this idea of radiative balance and apply it to real worlds, asking why some planets bake while others lie close to the CMB's deep freeze. Near Earth, when cold space hits, well, 120 degrees. So if a single astronaut can be half roasted and half frozen, what happens when we scale that problem up to an entire space station? Low Earth orbit is where cold space stops being an idea and becomes an engineering emergency every 90 minutes. The International Space Station circles our planet at roughly 400 kilometers up, racing through one full orbit in about an hour and a half. That means it repeatedly dives in and out of Earth's shadow. One moment, its huge solar arrays and modules are blasted by unfiltered sunlight. The next, the whole structure plunges into night, with the planet blocking the sun. This day-night cycling is relentless. There is no gentle sunset, only a hard switch. In full sun, surfaces that face the star directly can climb past plus 120 degrees Celsius. Metal handrails, exposed equipment panels, even parts of a spacesuit can reach temperatures that would easily boil water. But while the sun-facing side bakes, shaded surfaces that see only deep space can fall below minus 150 degrees Celsius, racing toward the background of the universe itself. This means the ISS is living inside a permanent thermal whiplash. It should be noted that the crew never feels this violence directly. Inside, the station is kept at roughly room temperature, in a range where liquid water and human life are comfortable. To pull off that trick, engineers had to turn the whole complex into a kind of artificial planet with its own controlled atmosphere and climate system. Radiators are the ISS's cold lungs. They are those white, wing-like panels extended away from the main truss. Hot fluid from electronics, life support, and experiments is pumped out to them. With no air to carry heat away, the radiators simply glow in infrared, dumping excess energy into space by radiation alone. In the hunt for alien life, we often talk about how a planet must shed heat to stay habitable. The station is doing the same thing, just on a metallic skeleton. Around the modules, multi-layer insulation blankets, those crinkly gold and silver wraps, slow the rate at which heat leaks out when the station moves into darkness. Each thin reflective layer bounces thermal radiation back and forth, so the interior does not instantly chill. At the same time, polished and white-painted surfaces reflect much of the incoming sunlight and even part of Earth's own infrared glow, cutting down on unwanted heating. Yet even here, racing above our clouds, the minus 270 degrees Celsius cosmic microwave background is quietly involved. Whenever a part of the station is in shadow and not looking at Earth, it sees that almost perfect cold and radiates toward it. The CMB is the ultimate sink waiting behind everything, from the ISS to a distant exoplanet. So it's time to find out the truth. If low Earth orbit is already this extreme, what happens as we leave our protective planet farther behind? Where sunlight weakens, radiators stare almost only at the CMB, and the cold of space begins to win. From Mercury to Pluto, a solar system temperature tour. So if low Earth orbit already lets the cold of the universe leak in, what happens when we step off the planetary stage entirely? To feel that tug of war between sunlight and the cosmic background, we need to tour the whole solar system. So let's begin with the planet closest to the fire. Mercury orbits just 58 million kilometers from the sun, with almost no atmosphere to spread heat around. In direct sunlight, its surface can bake above 400 degrees Celsius, hot enough to melt lead in some places. But while the day side is blazing, the night side plunges below minus 170. No air, no oceans, no clouds. This means one hemisphere faces a furnace, while the other stares into that near-perfect cold and radiates away its heat. Now imagine riding outward, past Venus, past our own habitable Earth-like world, and beyond the Goldilocks zone. As we travel, the sun shrinks and dims. The key rule is simple but powerful. As you double your distance from the sun, its light and heat drop by a factor of 4. Triple the distance, and the intensity falls by 9. It should be noted that this inverse square law keeps working all the way to the edge of the solar system, while the cosmic microwave background behind everything just sits there at 2.7 Kelvin, unchanging. By the time we reach Pluto, roughly 30 to 40 times farther from the Sun than Earth depending on its orbit, sunlight is more like a distant spotlight than a blazing star. Surface temperatures hover around minus 230 degrees Celsius. Nitrogen and methane ices can slowly evaporate into a thin atmosphere when Pluto is closer in, then freeze back out as it drifts away. Yet, even here, exposed ice still absorbs more energy from the Sun than from the cosmic background. The star is weak, but it still wins. But what about places the Sun cannot easily touch? In deep shadowed craters, under thick blankets of dust, or buried within comets, material can cool much closer to that 2.7 Kelvin floor, especially over millions of years. Optimistically speaking, if you were in the hunt for alien life hiding in subsurface oceans, this slow, relentless cooling would be a serious engineering challenge. Our probes feel this cold directly. Spacecraft like Voyager and New Horizons cruise through interplanetary space, where the environment is only a few degrees above absolute zero. Their electronics and radioisotope power systems generate precious internal heat that must be carefully managed, because the surrounding vacuum behaves like an almost perfect heat sink, stealing energy only through radiation to the dark. So it's time to find out the truth about the next step. If Mercury and Pluto are still ruled by the Sun, what happens when we leave not just our star, but all bright stars behind, and drift into the truly dark spaces between them? The quiet cold, between the stars. When we finally slip out between the stars, what does space itself feel like? We have left the warmth of any nearby planet or blazing surface behind, yet the universe does not drop us straight to absolute zero. The space between stars in our galaxy is not truly empty. On average, there are a few atoms in every cubic centimeter, mostly hydrogen, drifting in a vast, thin fog. Each of those atoms carries some motion, some heat, and they live inside a bath of radiation, starlight from billions of suns, high-energy cosmic rays, and the ever-present 2.7 Kelvin glow of the cosmic microwave background. This means interstellar gas does not all share one single temperature. Depending on how exposed it is, it can range from a few tens of Kelvin up to thousands. In the more diffuse regions, where you can see right through the galaxy as if through clear air, starlight and cosmic rays have easy access. They slam into atoms and electrons, keeping them relatively energetic. So while our instincts say deep space must be freezing, much of this gas is actually warmer than the surface of Pluto. It should be noted that this warmth is incredibly tenuous. You could fly a spacecraft through such a region and hardly notice, because there are so few particles to actually heat your hull. But while diffuse space is gently warmed by every nearby star, dense molecular clouds are different. These are the dark, dusty birthplaces of new stars and planets, where hydrogen clumps into molecules and grains of dust swirl like smoke. Here, layer upon layer of gas and dust act as a shield, blocking most external starlight and softening the impact of cosmic rays. Deep inside, the radiation field drops. Energy leaks away as infrared light, and temperatures can fall to around 10 Kelvin or even lower. That is just 10 degrees above absolute zero. Even in these frigid nurseries, the gas as a whole still sits above the 2.7 Kelvin background. The cosmic microwave background is like a universal floor heater you cannot switch off. Yet tiny dust grains, and especially well-shielded pockets, can creep closer to that baseline, cooling as they radiate into the dark and expand with the surrounding cloud. In the hunt for alien life, these clouds are paradoxical. They are brutally cold, yet they are exactly where new stars, new worlds, and potentially habitable systems begin. So, let's begin to picture the galaxy as a city at night. Bright downtowns cluster around each star, where radiation blazes and gas runs hot. Farther out, quiet, dark suburbs form in molecular clouds, where temperatures sink and future planets slowly assemble, all under the same faint, cold sky of the CMB. So it's time to find out the truth. If dense clouds can undercut the general interstellar medium, could there be places that slip even below the cosmic background itself without breaking physics? And what strange tricks would the universe have to use to get there? Colder than the universe? The Boomerang Nebula mystery. So if the cosmic microwave background is the universe's built-in thermostat, holding everything near 2.7 Kelvin, how do we explain a place that is even colder than that? There is one object that seems to cheat the cosmic rules. This is the Boomerang Nebula, about 5,000 light-years away in the direction of the constellation Centaurus. A dying star has wrapped itself in a ghostly cocoon of gas so cold that parts of it measure just 1 Kelvin above absolute zero. This means it is literally colder than the background glow left over from the Big Bang. So, let's begin with a simple question. How can any natural environment undercut the temperature of the entire universe without breaking physics? At the heart of the Boomerang Nebula is a red giant-like star in its final stages, throwing off its outer layers. As this gas rushes outward, it is not just drifting, it is racing away at more than 150 kilometers per second, expanding rapidly into the surrounding space. When gas expands this fast without being heated from outside, something important happens. Its internal energy is used to do work on its surroundings, and its temperature falls. It should be noted that we see a similar effect in everyday life. When we release compressed gas from a spray can, the metal chills dramatically as the gas expands. The Boomerang Nebula is that same physics, scaled up to a star-sized laboratory. But while a spray can warms back up in our room, the boomerang's gas expands into near-perfect darkness. The nebula is dense enough, and its dust thick enough, that much of the interior is shielded from external radiation, including the 2.7 Kelvin CMB. For a while, the gas is effectively isolated from the rest of the system. In this brief window, the adiabatic expansion outruns the cosmic thermostat, and the temperature plunges below the background. Does this violate thermodynamics? Not at all. This is a transient, out-of-equilibrium pocket, not a stable, eternal freezer. Over longer timescales, the story changes. As the expansion slows and the nebula thins, CMB photons and starlight can seep back in. Radiative heating will gradually push the gas back up toward 2.7 Kelvin, erasing the extreme cold we see today. Optimistically speaking, we have caught the Boomerang Nebula at a very special moment in its life, when local processes briefly beat the universe at its own game. So it's time to find out the truth. If nature can reach 1 Kelvin with nothing but a dying star and vacuum, how far can human technology go? In the hunt for alien life, we often talk about warm, habitable planets, but in the lab, we chase the opposite. By pushing atoms to billionths of a degree above absolute zero, we start to learn what the ultimate cold limit really is, and why absolute zero itself remains forever out of reach. Beating the cosmos. Labs colder than any nebula. So if nature's coldest nebula can reach 1 Kelvin, and our labs can go 1 billion times colder than that, what are we really doing to matter? We are, quite literally, beating the cosmos at its own refrigeration game. In a quiet vacuum chamber on Earth, physicists take a tiny cloud of atoms and shine lasers at it. That sounds like it should heat things up, right? But with laser cooling, the light is tuned so that atoms moving toward the beam absorb photons and get a gentle push backwards. Each photon steals a bit of motion. Do this from multiple directions, and the atoms slow to a crawl, their temperature plunging to millionths of a degree above absolute zero. Then comes evaporative cooling. Just like the hottest molecules in a cup of coffee escape as steam, the most energetic atoms are allowed to drift away from the trap. The atoms left behind share out less and less energy. This means the temperature can fall to billionths of a Kelvin, far colder than the Boomerang Nebula, far colder than any known natural region of space in the entire universe. At those temperatures, something extraordinary happens. Individual atoms lose their separate identities and merge into a single quantum wave, a Bose-Einstein condensate. Quantum behavior, usually hidden on subatomic scales, swells to macroscopic size. We can watch waves of matter slosh, interfere, and orbit inside the trap, as if we had slowed down reality itself just to take better data, but there is a wall we cannot break. Absolute zero, 0 Kelvin, is the point where all thermal motion would vanish. Why can we not reach it? It should be noted that every cooling step relies on removing some remaining energy. As the system gets colder, the energy chunks we can grab become smaller and harder to access. Reaching exactly zero would require an infinite sequence of ever finer adjustments and an infinite amount of time. Quantum mechanics adds another limit. The more precisely we try to pin down an atom's energy and temperature, the less precisely we can define when and how that measurement occurs. Time and energy blur together. So, let's begin to accept a subtle truth. Absolute zero is not a destination, only an asymptote we can approach. Compare that to space itself. Between galaxies, the cosmic microwave background bathes everything at about 2.7 Kelvin, a faint glow left from the Big Bang. Only special processes, like adiabatic expansion in rare nebulae, can dip below this floor, and only briefly. Our lab vacuums are tiny and controlled. Intergalactic space is vast, messy, and ruled by gravity, radiation, and chance. So it's time to find out the truth. If the average temperature of the universe is already so low, and still slowly dropping as space expands, what does that mean for the long-term fate of stars, planets, and life itself? Is the cosmos destined to slide forever closer to absolute zero, making even our coldest labs look warm by comparison? Is space getting colder forever? If space is already close to absolute zero, we might ask an even bigger question. Is it just going to keep getting colder forever? To answer that, we have to rewind the entire universe. Not just a few billion years, but all the way back to the Big Bang. In its first fractions of a second, the cosmos was unimaginably hot and dense, with temperatures trillions of degrees higher than anything our laboratories can produce. Space was not a cold, dark void. It was a blinding, seething ocean of particles and light, so energetic that atoms could not even exist. As the universe expanded, it did something very simple, but very powerful. It cooled. The same total energy was now spread across a larger and larger volume. Photons, the particles of light, were stretched by this expansion, their wavelengths grew longer, their energy dropped, and the temperature of the cosmic background fell. This means there is a direct link between the size of the universe and its average temperature. Physicists describe it this way. If you double the scale of the universe, you roughly halve the temperature of that background glow. When the cosmic microwave background, or CMB, was first released about 380,000 years after the Big Bang, space was not at 2.7 Kelvin. It was closer to 3,000 Kelvin, like the surface of a cool red dwarf star. Hydrogen and helium atoms were forming, and the whole cosmos glowed orange-white, almost like the inside of a very large light bulb. Fast forward a few 100 million years, the first stars and galaxies ignite. By then, the CMB has already cooled to just a few tens of Kelvin, colder than liquid nitrogen, but still setting the thermal stage on which those early structures evolve. Today, after more than 13 billion years of expansion, that same radiation has slid down into microwaves, giving space its familiar 2.7 Kelvin background. It should be noted that this cooling does not stop. In the far future, as galaxies drift farther apart, the CMB will sink below 1 Kelvin, then into the millikelvin range, then microkelvin, and beyond. In the hunt for alien life, that slow decline matters, because it shapes how long stars can shine, and planets can stay habitable. As the background temperature falls and energy becomes more evenly diluted, it gets harder for gravity to pull fresh gas together into new stars. Temperature differences flatten out. Engines, both biological and mechanical, rely on those differences to extract useful work. This is the idea of the universe's thermal death. Not an explosion, but a fade into darkness and near-perfect uniformity. So, let's begin to face a disturbing thought. If the cosmos started in a brief blaze of almost infinite heat and is heading toward an almost featureless cold, does that mean all structure, all stars, all life are just a fleeting spark between two extremes? And if so, what happens in the ages after the last star goes out? Hotter than stars, black holes, clusters, and cosmic fire. So if the universe is drifting toward a thin, cold darkness, where are the fires? Are there still places that laugh in the face of 270 degrees Celsius? There are, and they are some of the strangest environments we have ever discovered. On the largest scales, the space between galaxies in a cluster looks empty, but while it seems like a vacuum, it is actually filled with a ghostly gas called the intracluster medium. This gas is incredibly thin, far emptier than any laboratory vacuum on Earth, yet it is heated to tens of millions of degrees by the slow violence of gravity. As galaxies fall in and collide, shocks ripple through the cluster and compress this gas, and it responds by blazing in X-rays, while floating in a background that is only 2.7 Kelvin. This means that in a single telescope image, we can see matter at more than 10 million degrees bathing inside a cosmic sea just 3 degrees above absolute zero. Two extremes, sharing the same volume of space. It should be noted that this is not rare. Galaxy clusters across the observable universe host this hot plasma, silently glowing while the cold microwave background wraps around them like a universal freezer. But if clusters are hot, the regions around neutron stars and black holes are absolutely brutal. When gas spirals into these compact objects, it forms an accretion disk. Friction and magnetic turbulence whip the particles to hundreds of millions of degrees, hotter than the core of most stars. In the hunt for alien life, we usually focus on a calm Goldilocks zone around a quiet star, but here we find the exact opposite. Disks so bright in X-rays and gamma rays that they can outshine entire galaxies. Pattern interrupt. A black hole hotter than a star. Not exactly. The swirling matter around a black hole can be unimaginably hot, but the black hole itself is, in a very real sense, cold. According to Hawking's theory, black holes have a temperature and emit a tiny trickle of radiation. So it's time to find out the truth. For stellar mass and supermassive black holes, that Hawking temperature is far below the 2.7 Kelvin cosmic microwave background. They are effectively colder than the universe they sit in. So on small scales, space can be blisteringly hot. On the largest scales, it is ruled by the quiet, cold background that slowly drains away these differences over billions of years. Optimistically speaking, that cosmic refrigerator is what gives complex structure, planets, and perhaps life a stable stage to exist on for a while. And this leads to a deeper question. If how cold space is really a competition between local energy sources and the ever-present microwave background, where do planets like Earth fit into this thermal tug of war? So, would you actually freeze in space? So where does that leave us? If space is wrapped in this faint, 270-degree cosmic glow, what actually happens if a human body is thrown into it with no protection? We often picture an instant ice statue, frozen solid in a heartbeat, but while space feels unimaginably cold as a system, your body does not lose heat that fast. This means the real killers arrive long before the cold does. Within seconds, the lack of oxygen shuts down your brain. The near-zero pressure lets dissolved gases expand. Your lungs and blood vessels are under huge stress, and you lose consciousness in under 15 seconds. It should be noted that temperature is really about how fast particles are moving. In a vacuum, there are almost no particles to carry heat away. There is no air to conduct heat, no wind to convect it. So at the beginning, your skin would not feel like it was pressed against an icy metal surface. It would feel more like standing in a very cold, perfectly still room with one crucial difference. The moisture on your tongue, your eyes, and the surface of your skin would start to boil away into the vacuum. That boiling is not because space is hot, but because the pressure is so low that liquid water cannot stay liquid. As that moisture escapes, it takes some heat with it, cooling you slightly. After that brief phase, your body mainly cools by radiation, quietly glowing in infrared, bleeding energy into the blackness, and, ultimately, toward that 2.7 Kelvin background. So, let's begin to imagine a second twist. What if you are exposed to space near Earth's orbit in full sunlight? Now you are caught between a nearby star and the cold universe. The sunlit side of your body absorbs intense solar radiation, enough to raise its temperature, while the shaded side faces the 270-degree microwave background and radiates heat away. You could literally be heated on one side and cooled on the other, a strange thermal tug of war written across your own skin. This is why astronauts do not trust space is cold as a simple rule. Their spacesuits and spacecraft are not just fancy armor, they are mobile thermal management systems. Layers of insulation slow heat flow, heaters prevent dangerous freezing, and radiators carefully dump excess heat to space, so the interior can stay near a comfortable 20 degrees Celsius, even as the outside swings from roughly 120 degrees in sunlight to 150 degrees in shadow. So it's time to find out the truth about our own sense of temperature. Our daily idea of hot and cold lives in a tiny band, a local compromise between sunlight, air, and ground. In the wider universe, temperatures run from fractions of a degree above absolute zero to billions of degrees near neutron stars and black holes. Optimistically speaking, that contrast sets up our final question: how does this extreme thermal landscape shape where planets, and perhaps life, can actually endure? From fireball to freezer, what 270 really tells us. So if the universe is such an extreme thermal landscape, what does that average of about 270 degrees actually mean? It is more than just a fun fact about space being cold, it is a clue to the entire story of the cosmos, from fireball to freezer. So, let's begin by retracing our steps. We started by redefining temperature itself, not as how something feels to us, but as how fast particles move and how intensely they glow with radiation. Then we met the cosmic microwave background, this faint 2.7 Kelvin afterglow that fills every direction. This means the default setting of the universe today is a cold microwave bath just 3 degrees above absolute zero. On top of that background, every object has to fight its own thermal battle. In low Earth orbit, we saw how a spacecraft can roast on the sunlit side, while the shaded side plunges toward the cosmic baseline. No air, no atmosphere, just radiation in and radiation out. Farther from our star, across the outer solar system, sunlight fades, and planets, moons, and comets drift closer and closer to that deep cold unless internal heat or trapped air can hold the line. Between the stars, giant interstellar clouds take this even further. Dust and gas shield themselves from harsh starlight, cooling into chill darkness only a few degrees above the background. Yet, inside those same clouds, new stars and maybe future Earth-like planets will one day ignite. It should be noted that we have even found natural places, like the Boomerang Nebula, that are colder than the cosmic microwave background itself, using rapid expansion to radiate away heat. And in our laboratories, with magnetic traps and lasers, we have pushed atoms to nanokelvin temperatures, briefly beating the universe at its own game without ever touching absolute zero. But how did we get here? The early universe was unimaginably hot and dense, a blinding plasma where no atoms, no planets, and certainly no life could exist. As space expanded, it cooled, stretching that primordial light into today's microwave glow. Now the average temperature is 270 degrees, and as expansion continues, the background will keep sliding downward, slowly erasing temperature differences. Optimistically speaking, in the very distant future, stars will fade, galaxies will dim, and the cosmos will drift toward a thin, dark, almost perfectly cold state. So it's time to find out the truth about what cold space really is. Space is not just chilly like a winter night, it is a dynamic thermal battlefield where local fires briefly flare against an ever-cooling cosmic refrigerator. Every star, every galaxy, every nebula you have ever seen is an island of heat floating in an ocean that is right now just 3 degrees above nothing. In the hunt for alien life, that ocean matters, because the next question is this: in a universe racing toward the cold, where can warmth, planets, and life actually hold out the longest? Before the universe goes cold, your next step. So where does that leave us in this ocean of almost nothing, just 3 degrees above absolute zero? For a moment, pause and notice how your own intuition has shifted. At the start, cold space may have meant instant frostbite, ice crystals, a frozen astronaut. Now we know better. Space is not a uniform freezer. It is a delicate balance between starlight and a 270°6 background that never quite turns off. So let's begin one last thought experiment. Imagine you are standing on a dark asteroid, far from any star. No air, no atmosphere. Just you, your suit, and the slow whisper of the universe. At first, the sun is still a sharp point, warming one side of this lonely rock. But step into the shadow and wait. The light fades. The asteroid radiates its last stored heat away into the black, and very slowly, the temperature around you drifts down toward that cosmic background until the only warmth left is the heat you carry with you. How would you prepare for that? If you could visit any environment, where would you choose to stand? Low Earth orbit, with Earth blazing blue on one side and the sun burning on the other. A shadowed crater on the moon, locked at temperatures hundreds of degrees below freezing, or the edge of a cold molecular cloud, where new stars and planets are just beginning to form. This means you would have to design a suit not just for cold, but for brutal contrast. Sunward surfaces glowing hot, shadowed plates radiating toward 270 degrees Celsius. How would you move heat around your own tiny artificial world to keep yourself habitable? It should be noted that this question of temperature does not end here. If you want to go deeper, we can follow the trail to stranger places. What is the temperature of a black hole? And how does Hawking radiation slowly bleed energy out of the darkest objects we know? How does the James Webb Space Telescope hide its own warmth behind a vast sun shield and use cryogenic cooling so its instruments can see the faintest infrared light against that cold background? Or, if we rewind, how did we first detect the cosmic microwave background at all and realize the whole universe was glowing at 270 degrees? So it's time to find out the truth together. If this changed how you think about space, like, subscribe, and share it with someone who still imagines astronauts freezing solid in seconds. Leave your questions, your doubts, and your best misconceptions about space temperature in the comments, and we will use your ideas as data for future episodes. Optimistically speaking, we live in a brief, warm era between a fiery birth and a frozen future. Stars burn, planets orbit, and life thinks about its own place in the system before the long night. Understanding why space is so cold is really about understanding where we came from, and where everything is going as the last embers of the universe slowly fade into the dark.